Hello everyone, welcome to Scholar Lab. Our simulations can transform your teaching approach, making lessons much more interactive and captivating for your students. Scholar Lab is a distinctive virtual laboratory that brings intricate STEM concepts to life through engaging simulations. This tool is crafted to aid students in comprehending and applying scientific principles in practical situations. In this simulation, we are taking our students on an engaging journey to explore the gas behavior under different conditions which would be difficult to replicate in our traditional school lab. Let me open Kinetic Theory of Gases simulation for you. Here is the game plan. The main objective is to understand the ideal gas law and the degrees of freedom of gas molecules through real-life examples and hands-on experiments. Students will also explore how gas behaves when we alter the temperature, pressure, and the volume of the closed container. Finally, they'll observe how mercury in a U-shaped tube reacts to the pressure changes and see how gas volume and pressure depend on temperature in different weather conditions. Let me close this game plan. This simulation offers you a range of perspectives. By using your mouse button, by click, hold and drag, you can view different angles of our physics lab. Or else you can use this bottom right button to view that in different angles. F for front view, T for top, R for right and L for left. Unlike typical lab experiments, this one gives us the freedom to explore the setup from every angle, which deepens our understanding of the science concepts. Here we have 4 parts: concept, Boyle's law experiment, gas laws application and finally quiz. Under concepts, we are going to explain ideal gas behavior and degrees of freedom. Let's begin with basics. Imagine pumping some gas molecules into a closed chamber. Here we have gas A and gas B. Let me fill that to the chamber by clicking on it. By keeping these parameters constant, you can observe the gas molecules changes by altering the other parameters. Or else, you can check this no constraints to view how other parameter changes affects the behavior of gas molecules. Now let me show you how the temperature affects the gas particles. Upon clicking on this low temperature, which is absolute zero, the gas particles becomes motionless. Upon releasing it, you can see the gas particles are moving. By clicking on this graph, it will show you the graph between pressure and volume or pressure and temperature and volume and temperature. Let's see how this graph works. I'm keeping at no constraint mode and I'm trying to change the temperature now. I'm heating the container. As you can see, temperature versus volume curve, how it looks like. Similarly, pressure versus temperature and volume versus temperature are changes accordingly. Let's keep the temperature as constant. Let me change the volume of the cuboid by clicking on these arrow marks. As you can see, The graph is plotted accordingly. By clicking on these different graphs, you can teach them very clearly how these parameters are affecting the behavior of gas particles. Let's dive deeper into the concept of degrees of freedom. Degrees of freedom, which plays a crucial role in understanding the behavior of gas molecules. Here we have three types of gas molecules. Those are monatomic, diatomic, triatomic, linear. First, we'll explore monatomic. As we all know, monatomic is the simplest gaseous particles. This will have only 1 degree of freedom, that is translation. I'm clicking on translational to show what are the motions these atoms or molecules will have. These gases consist of single atoms, meaning they have 3 degrees of freedom, one of each directions which they can move, x, y and z. In this case, all energy is stored as a translational kinetic energy, as these atoms do not rotate or vibrate. This makes the monatomic gases the simplest type to understand. Once you have found out the correct answer, how many degrees of freedom or how many motions that particles will have, you can click on submit button to check whether your answers are right or not. Let me go to diatomic. Diatomic molecules like oxygen or nitrogen. Here we have the molecules consist of 2 atoms bonded together, as you can see here. These gases have more complexity than the monatomic. Like monatomic gases, diatomic molecules can move in all 3 directions, like this. For translational, x-axis, y-axis and z-axis as well. But in case of rotational degrees of freedom, unlike monatomic gases, diatomic molecules can rotate around 2 axes perpendicular to the bond axis. This adds to rotational degrees of freedom to the molecule. Like this, and another rotation is like this. If I'm clicking on 1 more degrees of freedom and submitting the answer, see, it is showing us the hint which is correct and which is wrong. And also it tells us why the rotational degrees of freedom is wrong. In this way, you can check the answers through this immediate response. Let me show you diatomic linear also very quickly. As usual, we have translational degrees of freedom in all 3 directions. And in case of rotational degrees of freedom, for linear molecule, we all know that we'll have 2 rotational degrees of freedom. And for vibrational, we are only producing for stretching motion. Other motions will get covered up later. Now, let's turn our attention to a classic experiment using YouTube. This simple yet powerful setup vividly demonstrates how fluid level changes affect the pressure difference. Let me fill the mercury to the U-tube by clicking on it. Initially, mercury levels in both the arms are equal, indicating that the pressure on both the sides of the tube is balanced. And this is our starting point. As the height difference changes, the pressure will also get changes. Let me click on the up arrow to increase the height of one side of the U-shaped tube. As you can see, the pressure will also get changed. This is because, according to the Boyle's law, as you decrease the volume or increase the volume, the pressure within the side of the tube decreases or increases accordingly. Because the Boyle's law states that the pressure of a gas is inversely proportional to the volume. And we are not stopping here. You can take the readings by clicking on this Take Reading button, and once you have taken the enough readings, this Show Graph button will give you the reading and the graph of this Boyle's law, like we did in the ideal gas behavior. Let me go to the third part of this simulation, which is real life application of these gas laws. For instance, when you inflate a bicycle tire, you are decreasing the volume of the air inside the pump, which increases the pressure forcing the air into the tire. Let's imagine this kind of sit. We are bringing our students to the garage to fill the air into the bicycle. Here we have the parameters of temperature. At the time of filling the air, you can change the temperature from 4 degrees Celsius to 50 degrees Celsius. Let me set 4 degrees Celsius for now. I'm setting the temperature by clicking on this, the pump. It will increase the pressure and the air is getting filled into the bike tire. Everything seems perfect. Let's get started for our bike ride. But the weather can have a significant impact on the tire pressure as the day progresses and you encounter different conditions. Let's explore how the Boyle's law comes into play. Let me take the bike on summer day by clicking on it. The temperature here is 45 degrees Celsius. As you take the bike into the sunny environment, the temperature rises. The pressure increases can be significant and potentially exceeding the tire's recommended maximum pressure, which leads to the risk of blowout or decreased performance, as you can see here. Let me show you one more example here. Let me take this bike at the same temperature, but the environment temperature is that. Now let me take that on winter day. As the temperature is not more significantly high than the temperature of the gas filled, it will not show much difference in the bike tire inflations. So nothing noticeable happens. You can also reverse the scenario. Like what if you inflate the tire at the warmer temperature, like 50 degrees Celsius. What if you are taking a ride in cooler conditions? For instance, let me take the ride at winter, which is having minus 10 degrees Celsius. You can use this button to fast forward the bike ride and see how the bike affects. As the gas pressure in the tire decreases due to the low temperature outside, when the temperature of the tire is significantly lower than that of what was filled at, it results in tire flattening, which is shown here. And the fourth part of the simulation is quiz. This interactive quiz will cover the concepts we have explored in the simulation. This will give us the understanding how well the students understood the topic. Here we have a set of 5 questions. After attempting all 5 questions, you can click on the submit button in the end to check the score and the correct answers. I'm checking the correct answer by clicking on check answer button. Also, you can click on this explanation button to view the solution or the explanation part of the question. In conclusion, by engaging with this simulation, students gain an hands-on understanding of Boyle's law and other gas laws. They'll see how pressure and volume are inversely related, how the gas particles are behaving with these parameter stages, and how this principle applies in both lab and the real world scenarios. They'll understand this very, very deeply. And kindly encourage them to experiment with these different volumes and pressure deepens their grasp of their gas behavior. Making this fundamental experiments will deepen their knowledge. And also making this fundamental law both intuitive and memorable. Happy learning. Thanks for watching.